In this video, we're going to talk about a couple of different special types of field extensions, and those are finite extensions and algebraic extensions. Let's start with algebraic extensions because the idea of that builds on concepts that we discussed in previous videos. So just as a reminder, recall, if f is a field and E is an extension of f, and A is an element of E, then A is algebraic over F. And let's underline all of that because that entire thing is what we're defining. Algebraic over F if A is a root of some non-zero polynomial in F adjoint X. So that's what it means to be an algebraic element. But what about an algebraic field extension? Well, here's the definition. Let F be a field and let's let E be an extension. Then E is algebraic over F in other words, E is an algebraic extension of F if every element of E is algebraic over F. Okay, so that's what it means to be an algebraic field extension. So for example, we've seen quite a few of these already. One example is Q adjoin square root of 2. That's algebraic over the rationals. And you may think, oh, that's obvious because we just took the rationals and we adjoined the square root of 2, which is definitely algebraic over the rationals. But that actually takes a little work to prove that this is an algebraic extension. So here's how you prove it. At least one way to prove it. There are easier ways of proving it, more elegant ones that we'll talk about later. But here's one very straightforward nuts and bolts way you can prove that Q adjoin square root of 2 is algebraic over Q. So we know Q adjoin root 2. That's the set of all A plus B root 2, where A and B are in the rationals. So we need to prove that every number of that form is algebraic over Q. So one way that we could do that is we could say, well, we already know that the rationals are algebraic over Q. So we already know A plus B root 2 is algebraic if B is equal to 0. That is if I'm dealing with just a pure rational number, because then I could just say, well, x minus A, that's a polynomial with A as a root. Done and done. Okay, but what if B is not equal to 0? Then I might use the following routine to find a polynomial, create a polynomial that has A plus B root 2 as a root. So for example, let's say x is equal to A plus B root 2, and I'm going to see if I can massage this into a polynomial equation that has A plus B root 2 as a solution. So I'll start by pulling the A over and get x minus A equals B square root of 2, and then square both sides. X squared minus 2ax plus A squared equals 2b squared. And then that gives me x squared minus 2ax plus a squared minus 2b squared. I believe that will be a polynomial. It's definitely non-zero, having a plus b root 2 as a root. It is in Q adjoint X because every coefficient, 1, 2a, and a squared minus 2b squared, each of those is rational. So I now have a non-zero polynomial in Q adjoint X that has A plus B root 2 as a root. Note that I'm not claiming this is irreducible. I don't need to show that this is algebraic, A plus B root 2. I only need to show that it is a root of some polynomial. And if it is a root of some polynomial, then there will be an irreducible somewhere. I'm just not necessarily claiming it's this. Okay, so anyway, that shows that every such element is algebraic over the rationals. Therefore, this field extension Q adjoin the square root of 2, that is an algebraic field extension of the rationals. You could use a similar technique, for example, to show that the field of complex numbers is algebraic, but not over the rationals, over the reals. I'll leave you to prove that one yourself. Okay, however, the field of real numbers is not algebraic over the field of rationals. And we're not going to prove that in this video, but the proof is something you could do. You just have to show that there exist real numbers, which are not solutions of polynomial equations in Q. Okay, so that's the idea of an algebraic extension. Now let's come over here and talk about finite extensions. So this is more of a linear algebraic concept about field extensions. Here's the definition. Okay, so first of all, recall that if f is a field and E is an extension of f, then the degree of E over f is the dimension of E as a vector space over f. And it's usually written as E colon f. And we say that E is a finite extension of f if that degree or that dimension is finite. Okay, so that's what it means to be a finite field extension. Notice this doesn't mean that E is a finite field. It doesn't mean it's a field with finite limiting elements. It just means it's a field whose dimension as a vector space over f is finite. Okay, so for example, Q adjoin the square root of 2. This is a finite extension of the rationals, and we saw earlier that Q adjoin root 2 is the set of all numbers a plus b root 2, where a and b are rational. So because of that, Q adjoin root 2, this is actually a vector space over the rationals, and a basis for it is just 1 and square root of 2, because Q adjoin root 2 is just made up of rational linear combinations of those two elements. So the degree of this field over the rationals is just 2. All right, and similarly, I could think of the complex field as an extension of the real number field, and the degree of that would also be 2. I'll leave you to figure out why. However, the dimension of the real numbers as a field extension of the rationals, or the degree of the reals over the rationals, is infinite. To prove that, you could use a countability argument. You could say, well, suppose that the reals had finite dimension as a vector space over the rationals, then there would have to be some finite basis, and every real number would be expressible as a rational linear combination of elements of that basis. I won't say more about that because I want to encourage you to try and prove that on your own, but rest assured that degree is infinite, so that is not a finite field extension of the rationals. Okay, so there's one major result we're going to prove, and I'm going to reserve it for the next video, but I'll go and write it here. So there's a theorem that every finite extension of f is algebraic over f. In other words, if I take f and then take a finite extension of f, then every element of that field will be algebraic over f. We'll prove that in the next video.